So this is where we left off last time. And we were looking at what? So we were saying that this is Usain's distance as a function of time. And we were saying that, so is the rate of change of distance changing or constant? Is the rate of change of distance changing or constant?
Changing.
Changing, and you can see by a curve. But how can we see it as constant also? How can we see the rate of change as constant?
Look at a small enough moment.
Right, so, and we talked about a moment, right? Rate of change at a moment means a moment, and that's like over here in the right graph. A moment is like an interval of time or interval of your independent variable that's small enough so that you have what we call local linearity, right? So if you zoom in close enough onto a curve, it eventually will start looking straight. If it's a conventional continuous function. So we were looking at, in the moment, we were looking at, accumulating. So we're going to start talking about accumulation, right? So we're looking at the accumulation of distance at a constant rate of change within the moment, right? So accumulation of distance within the moment at a constant rate of change. And so we've been working at a constant rate of change, right? We came up with we talked about how changes in the dependent are proportional to changes in the independent, right? If you have constant rate of change. And then we can use that to build up what our equation of a line, which we took y final plus the change in y, right? Which was m times the change in x. So in doing that, we're able to represent, so I'll pause it here. This represents every correspondence point of time and distance in this moment, right? So given any time in this moment, x, this will tell us the corresponding distance he's run from the start. Okay, so what we're kind of the big endeavor then that we're like knocking on the door of here and we're about to launch here is the idea of you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. Okay? So you know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. So this is kind of in the next 2 weeks or so. This is going to be our journey. And this is really one half of calculus, right? So this is like the one of the questions, one of two problems or questions that we ask in calculus. If you know how fast something's changing every moment, can we determine, figure out, or model how much of it we have at every moment? So to get us started on this, to kind of make sense of the functions that are involved with this, I have a handout that you should go to Canvas, and the first page looks like this. There's 3 graphs, one on the left, 2 on the right. And if you go to the module with the handouts, so if you go to modules, and go to class worksheets, the first one, bathtub and oil leak. Bathtub and oil leak. So I want you to pull that up on your screen, or if you can print it out quickly, you could print it out quickly. And I'm going to break you into rooms, and you guys are going to work on that, just the first page. Mine is loading here. So the first page has this context here. The tub has 2 gallons of water in it. The tub has 2 gallons of water in it, and the faucet is turned on such that water flows into the tub at 1.5 gallons per minute. Let T be the time in minutes since the water was turned on. And for each, we want to label the axes with correct units and sketch the graph according to this setup. So read carefully. So number of minutes is always your x-axis, okay? And then these descriptions are telling you the quantity that goes on the y-axis. So this is the rate of change of amount of water in the tub. This is the number of gallons added to the tub at t minutes, and the number of gallons in the tub at, or I should say after. So this was, you could say after t minutes, instead of at, okay? All right, so is the task clear? According to this context, you're going to sketch these 3 graphs. So any questions about that task? Okay, is everybody back? Yeah, looks like we're back. Okay. So how did it go? Let's go. Oh shoot, I shouldn't have done that. Who was in? Did you have room numbers? Do you remember what room you were in?
I was in room 1.
All right, so you were with who?
Donna.
All right, you and Donna, you're room 1. So how did the rate of change graph go? So the rate of change amount of water in the tub after t minutes.
We drew a horizontal line at y equals 1.5.
Y equals 1.5.
We assumed a constant rate of change.
Is it here?
Yes.
Okay, this is what breakout room number 1 is proposing. What about the rest of you? Agree?
Agree, yes.
Okay, we got 1 agree.
Do we need to tell you what we labeled the axes?
I figure you got that. So minutes, and what did you put for this, Donna?
The amount of water in the tub in gallons.
This is the amount of water in the tub in gallons here?
Per
Yeah,
minute.
the Y values.
Per minute. Gallons per minute.
Oh,
Yeah, this is not the number of gallons, right?
mm-hmm. Oh, yeah.
So this is gallons per minute, right? So these numbers are gallons per minute. I think you knew that. You just got maybe jumped ahead a little bit. Okay, cool. So breakout room number 2. Who was in number 2? Okay, Sarah, who are you with?
Yeah, that was me and Ashley.
Okay,
Sorry.
no problem. Okay,
Yeah, I
Sarah.
don't know if it was 2 or 3.
All right, whatever. So Sarah and Ashley, it doesn't matter. So Sarah and Ashley next. So this is the number of gallons added to the tub after t minutes. What did you guys come up with for that?
We had a straight line, I guess, we started at 0, 0, 0, because nothing's being added in the first minute, and then we added like 1.5 gallons each time.
So each minute you got 1.5 gallons like this? Is that what you mean?
Yeah,
Yeah.
added, yeah.
Okay. And so what's the graph then?
It's a line at 1.5x. Y equals 1.5x.
Like this?
Yeah.
Is that with the rest of you? Agree?
Agree.
But I thought there was, how many, wasn't there 3 gallons to start with or something?
There was 2 gallons to start with, but this is asking how much is added every minute. So we didn't technically add any gallons at 0 minutes.
So this quantity does not start at 2, it starts at 0.
Mm-hmm.
Did all 3 groups get that? So yeah, this is a really important point. It's easy to, if you're rushing a little bit, you're not thinking, it's easy to do this, right? Did any groups or people start this way and then realize the error?
That was me.
Yeah, no, and that's many students. Okay, that's many students. So we really got to be tuned in on what the quantity is that we're doing. Then what about the last graph? So Elizabeth and who was left? Elizabeth and
It was me and Elizabeth, yeah.
oh, Yasra. Yeah. So what about the last graph down here?
We said it's the same as the one we just did. It's just shifted 2 units up.
Okay, so that's the one that starts at 2, the dotted
Yeah.
line that I drew.
Yeah.
Okay, very good. All right, so this is a really simple, this is kind of a really simple kind of synopsis or an example of the 3 key functions that are involved in this this endeavor that we're about to embark upon, which is what I said before. You know how fast a quantity is changing at every moment. You want to know how much you have at every moment. So let's look here and let's kind of summarize that. And so these are the graphs that you guys got? Everyone got? All right, so you know how fast a quantity is changing at every moment. Which of these three graphs would represent that? You know how fast a quantity is changing at every moment. Exhibit A, B, or C?
A.
Exhibit A, right? The rate of change function. So every moment means we have this time going by in minutes is broken. We can think of it broken up into many, many moments of time. And in every moment, we know what the rate is. That's what this function tells us. Makes sense, right? So this is our rate of change function. This is, you know how fast a quantity is changing in every moment. Okay? You want to know how much of it you have at every moment. So which of these graphs is, you want to know how much you have at every moment?
C.
Okay, someone says C. What about B?
That's not like your total, it's just how much you've gained, I guess.
Right. But isn't it kind of like, it's like very close sibling, right? I mean, these are like twins, right? They're so close. They're both talking about what we call accumulation of the quantity. So this one is net accumulation. So every minute we're tracking how much change, total change, net change, I shouldn't say total, but the net change since the starting point. So it tracks the net change in a quantity since a chosen starting point. So we're starting at 0 here, we're choosing 0. And so the values of this function then, what tell us how much water has been added at that number of minutes. And that's what we call net change or net accumulation. And then, like she said, this is the total accumulation function. So this tracks the total accumulation of our quantity. This is like truly how much we have. But that net accumulation is so close, right? It's like we know it's just that initial value away, right? So it's like this, we call this all the accumulation from before. That's the only difference between these two, is that this one includes all the accumulation from before we started tracking it. This one does not. This one just tracks how much change in the quantity since our starting point. Okay, so these are the key players in terms of functions. You know how fast a quantity is changing at every moment. You want to know how much of it you have, whether that's net accumulation or total accumulation. Okay, so here we go. So that's kind of an overview of the functions and what we call them, right? So this will be to give us some language, right? Give us language as we're talking about this stuff. Okay, so now let's look at this new context. So function R gives the rate of change of volume of oil expelled per day by a rig that begins to leak at t equals 0 days. So maybe this is a oil rig in the ocean, and it starts to leak. And it blows a hole in it or something. And so now this is giving us what the rate of change in meters cubed per day of oil leaking into the ocean. So can you imagine a function that would give the total amount of oil expelled X days after the rig started to leak? So could you make a quick sketch of that? I think, no, that's... So could you sketch that? Well, I mean, now you've seen it. I thought I put a blank axis up next, but I actually put the function. So so if this is going down, why is this always going up, right? If this function is going down here, why is this going up?
Because the graph on the left is showing the graph of the rate of change.
Okay.
So like the rate is decreasing, but
Okay.
that doesn't mean that we're losing any amount.
Okay. So what determines whether we're losing or gaining?
If it's like below or above the x-axis, the rate of change graph.
Okay. And so our rate of change is above, which means what?
We're gaining.
We're gaining because the rate of change is
Positive.
right. So we have positive values of rate of change the whole time. Therefore, the accumulated oil in the ocean is always
Increasing.
going up, right? Yeah, increasing, going up, exactly. It's going up at different rates, right? So it's at the beginning it's going up the fastest, and then here it's going up the slowest, but still going up, right? Still going up, and then it starts to go up faster again. Okay, so yep. So our endeavor in the next few weeks will be to develop a quantity like V. And is this net accumulation or total accumulation?
Total accumulation.
Okay, he wants total accumulation. And why, Richard?
Because the question asked for the total amount of oil.
Okay.
So that's the total.
Well, had I not asked that question and just threw this graph up here? Okay, so this is the oil expelled per day. The oil expelled per day by a rig that begins leaking at t equals 0 days. So had I not said total amount, what would you say? Would you still say this is the total accumulation of oil? Or net accumulation of oil?
I think you'd say total because it starts at the 0 days.
Mm-hmm. And what would be different about the net accumulation, right? So starting from 0, what would be different about the net accumulation of oil or the amount added since time equals 0? How would that function be different?
I think it would be the same.
Okay. Anyone else agree with Donna or disagree?
I will agree.
I think I would say it's like the net, because like I would assume you start off with oil.
So it begins leaking after 0 day at t equals 0. This is when the rig starts to leak at t equals 0. So that would imply that there's no oil in the ocean before that.
Oh, okay, I see what you mean.
Does that make sense?
Yeah.
So the conclusion was correct. This is both, right? If there's no accumulated amount before we start tracking it, then net accumulation and total accumulation are the same function. Does that make sense? Because we're starting from 0. So the total amount that you have is the same as how much change you've had since 0, because there was nothing before. Is that cool with everybody?
Sounds good.
Yeah. So so in this particular case, the net accumulation and total accumulation is the same, and our endeavor is, given a function like this, can we determine, so this is just the graph, right? Can we determine maybe a formula or some exact representation of this volume accumulation function given the rate of change function? And that's no small task. Okay? What makes it a difficult task? What is it about this rate function that makes coming up with this accumulation function difficult?
It varies.
The rate varies, right? If this were a constant rate, like the tub problem, then we could just draw it, right? We have a linear accumulation if you have a constant rate of change, like we had in the tub problem. As soon as the rate varies, well, now this is much different, and this takes a lot more work. But we want to leverage what we know about constant rate of change to help us. So we're going to use constant rate of change in order to, it's a big part of this process. Okay, so how does the statement, so we're not looking at the rate of change graph, how does the statement R sub V, oh, and by the way, so R stands for rate, and the subscript V meaning we're going to do the accumulation of volume, right? So our volume is our accumulation function. So we're going to use R subscript V to mean exact rate of change. Okay, so how does the statement R of V 0.7 equals 9.68 relate to this graph? So how does this symbolic statement, how is it represented, or how is it, what is it about that graph that has to do with this? What's the connection between this symbolic statement and this curve?
Well, to me, it sounds like it's just the points on that curve.
Points?
Yes, represented as a point.
Okay, so I didn't know if you said point or points.
Point.
Point.
Singular.
A point, singular. Okay, cool. Yeah, it's a point on the graph, exactly. 0.7 and 9.68. It's this point right here. That at 0.7, that point tells us that at 0.7 days, the rate of change is 9.68. Okay? And so remember we talked about what local linearity. So we now want to bring our knowledge of moments into this. So what we want to, it's not at 0.7, because at 0.7, if you freeze time at 0.7, no oil is being added in, right? It's about a little change at 0.7 where oil is flowing in at that rate. So we say, so what this means is that at the moment, 0.7 days, the oil leaked in the ocean is essentially constant at, the rate is essentially constant at 9.68 meters cubed per day. Okay? And what does that mean? What does it mean that we have a constant rate of 9.68 meters cubed per day? Elizabeth, what do you think?
Wouldn't it be like at those like times in the moment
Uh-huh.
that the amount of oil leaking is like 9.68 like meters per, so like at those moments that's like the rate of it, so like
Okay,
it
but
was to be constant,
I'm getting
and
that.
that's how much would be leaking per day.
Okay, so in the moment, do we have a day that goes by? In the moment?
No,
Okay.
it would be like any like change in like day for like any time period in terms of days.
Okay, that's a good start for any time period in terms of days. In the moment, what does the number 9.68 mean? And this could be to somebody else. Ashley, what do you think?
That the volume of oil is being expelled at 9.68 meters cubed.
Okay, and
Moment.
that's true. That's what this says. And I'm asking, what does that mean, right? So what does it mean that we have this constant rate of 9.68 meters cubed per day?
That oil's leaving? I don't.
Anybody remember? Today's the day. Today's the day we're going to learn it. Everybody's going to learn it, and we're never going to forget it.
For a small moment in time next to 0.7 days,
Okay.
the The change in variation of oil leaks is 9.68 times. That's change in time.
Good. Okay, here we go. So given a variation in days. Now, what do we have to qualify? So now we have to stay in the moment, right? We have to stay in the moment. So how do we have to qualify that variation?
Given a small variation.
It's got to be within the moment, right? So it's going to be a small variation. So given any small variation in days, he said, the variation in oil leaked is
9.68 times
Did I
as
s-
large as.
did I-
Or,
T. So I'm calling this T. So 9.68 dt. Or dV equals 9.68 dt. So not only does this tell us a lot more than how much oil leaks out in a day, that is kind of an irrelevant conclusion, right? Because the rate is constantly changing. So to talk about how much leaks over one day is totally irrelevant because the rate is continually changing and changes a whole lot over one day. That's why this definition is so important. We have to be able to know how much oil leaks in any amount of time, because the only amounts of time that are going to be relevant are very small variations in time. A day going by is irrelevant for this rate. What's relevant is variations of time within a moment, very small moment, right? So given a small variation in days, within the moment at 0.7 days, the variation in oil leaked will be 9.68 times that variation in time, dt. So I should have written so our small variation in time days is dt. Then the variation in oil that we'll get is going to be 9.68 times dt. That's what it means to have a constant rate of change. It doesn't come easily. I know. It doesn't come easily. So that's why we keep working on it. Okay, so let's press on here. So here is the moment at 0.7. And so what do you notice about, so if I look at this small moment here at 0.7, what do you notice about the rate? Constant or changing?
The rate's constant.
Is that what this is showing here? Is this showing that the rate is constant? It's showing linear. Is this showing that the rate is constant?
The rate is like slightly decreasing.
Yeah, so this is the
intervals of time.
Right, this is the rate graph, not the accumulation graph, right? An accumulation graph being linear means a constant rate. But if the rate graph, this rate graph is still decreasing in the moment. So we're going to have to revise this. So what do we need this to look like to assume a constant rate in the moment?
Graphically, it would be a horizontal line.
Right, exactly. We're going to need a horizontal line, right? So to say that it's the rate of change in this moment is 9.68 meters cubed per day means a horizontal line for a rate graph. So we got the local linearity, but we need a constant rate. So that rate is still decreasing. So this new blue graph can represent the rate of change of the moment, the rate of change of the moment, the 9.68. Okay, so now we're going to use the stuff we've been learning here, and so we've got the rate of change in this moment, and now we want to kind of make some progress at how much do we have, how much oil do we have. Okay, so suppose that at 0.7, so much that this is how much oil has leaked thus far. So the total amount leaked into the ocean, 13.15 meters cubed. So under our assumptions, what would dx and dv be for finding v of 0.70013? And what would dx and dv be for finding a v of 0.702? So how about, let's go with this one first. So if we're talking about finding, knowing that the volume at 0.7 was 13.15, we're interested in the volume at 0.70013. What would dx and dv be?
Wouldn't dx just be 0.00013?
Okay, she wants 0.00013. The rest of you agree with that?
Sounds good.
Is it 3 zeros? Yeah. Okay. And then what about dv? So given this change in x, what is the resulting change in volume?
9.68 times dx.
Right. What's our meaning for the 9.68? Given any change in time, the change in volume is 9.68 times the change in time. And how does that help us find? And so let's start drawing this here. So where's 0.7 is right here. And what was the volume at 0.7? 13.15. Is that right here? Do I have that right? My eyes are going bad. Okay. And so dx, 0.00013. Where does that put me? This is 0.001. So 0.00013 is like what? Is that 13% of the way to 0.001? So it's pretty short right there, like that. Okay, and then we have a change of, anyone crank this out? We got a calculator? Anyway, it doesn't have to be perfect, but when x changes that much, then we have the change in volume of dv, which is our mdx. Oh, I think we're using t, right? Sorry. Oh, I guess I went back to x. So at one point it was, yeah. So anyway, t's got turned into x's. Okay, so we're going to stick with x. So dv equals our mdx. Okay, and then how does that help us find v of 0.70013? How will we find that?
We add dv and then our y initial, which was 13.15.
Right, it's going to be the right v initial plus change in v, right? V final is v initial plus the change in v. So we're going to add the 13.15 plus whatever we got for that, and we get v final. So then
It was 0.0013-ish for DV.
right, because it's basically almost 10, right? So it should still be 0.00, maybe 1.2 or 1.3.
1.3.
Okay. And so then we add that on, and we get the v of 0.70013. Which is the what? the 13.15, V initial, plus the change in V, we found by MDX. So look, we were given the rate of change, we knew the rate of change, and we just kind of modeled a little bit of accumulation. We figured out how much we had over this 0.00013 seconds, how much we gained, how much we accumulated, that little bit. Okay, and so we could do that again for 0.702, and that will give us something. So let me erase this. So what's the change in x here? Let's do it fast. What's the change in x for 0.702?
0.002.
Good. And where is that? Is that right here? Yep. So there's dx equal to 0.002. And what will dv be? Elizabeth?
It would be 0.002 times 9.68.
Right. Anybody? So can someone, while I'm writing, can someone crank that out? M times dx. So is that 0.02 or 0.019 or something?
0.019.
0.019. So I think that's almost okay. So that's going to put us right about here.
A little far.
Did I go too far? This is 0.0.
Yeah, that's right.
Yeah.
0.02. Right. We don't like 0.0019. Or it's practically 0.02.
Yeah, because this is 0.02, so I'm almost to 0.02 up. Okay, and then so then V final, V of 0.702 is approximately what? Quick. 13.15 plus 0.019. 13.169. Check my math. And why did I say approximately? Why is this not exact?
We have local linearity and not constant or actual linearity. So it's not
For what quantity are you talking about?
Is it not both quantities of volume and volume dispense in time? There's not a local, or it's a local linearity relationship between the two.
So local linearity is what makes it approximate? Is that what you're saying?
Yes.
And you're talking about local linearity of this graph or of this graph? So what assumption did we make along the way that result in this being approximate?
This was like a small enough moment.
Yeah, so even in this moment, right, the rate is still, we see the rate is still changing in this moment. And we assumed that it was constant. So that assumption that it was constant is going to make a little bit of, it's going to be, a little bit off, right? A little bit off from the actual true decreasing rate. Okay, so we're assuming a constant rate, and so then we're assuming that we have all these correspondence points in between. I want to write an expression that models all of those correspondence points from here to here. How can I do it? I want something that represents every correspondence point. Not just the one at 0.7 at x equals 0.702. Something that represents every correspondence point. Say that one as an arbitrary pick. Any ideas?
Just one question. You mean correspondence points in this one moment, correct? Not
Yeah,
every
in this,
moment.
for these correspondence points right here.
Okay.
Yep. As soon as we move out of this moment, we'll be at a different rate, and we can't maintain this linear increase anymore. So I just want to represent all the correspondence points like between the 2 points that we just found. How can we do it? Donna, any idea?
We want it to tell us the volume, right?
Uh-huh.
So we'd say like whatever volume we want is equivalent to the initial volume of our first point.
Okay. And how do we say whatever volume we want? How do I write whatever volume we want symbolically?
V.
Well, V is the name of the function. How do we get any volume that we want? So does V equal something? Does that equal a number?
No.
No.
Like function notation, maybe?
Does that give us a number of an amount of volume, function notation?
We could do like B of t.
Okay, so but we weren't using t anymore.
Oh, sorry. You wrote x, yeah.
So v of x? That okay. So v of x. And Donna, what were you saying about that? So this is what? This is like final volume.
Mm-hmm.
At x.
Mm-hmm.
What were you going to say? You were about to say something.
Also, would say that equals to the initial volume.
And how do I represent that symbolically?
V of 0.7.
Okay.
Plus 9.68 times dx.
Okay. But my function is not a function of dx. It's a function of x. But you're right. That's what we want here. We want dx. But I need it as a function of x, not dx.
9.68 times the quantity x minus.
Yeah. So
0.002.
what is dx for any point? Dx equals
X minus 0.7.
That's what you said, right, Richard?
Oh, I said x minus 0.002.
Okay, you had the right idea. But the starting x is 0.7.
Oh, yeah.
So, but yeah, you had the right idea. So what will it be? Starting volume plus 9.68?
Times x minus 0.7.
Remember doing this, everybody?
Mm-hmm.
That represents all correspondence points given a starting point and the rate of change, right? So we let x vary first by the amount of dx, which is x minus 0.7. Then the corresponding change in volume will be the rate times that dx. Or 9.68 times x minus 0.7 to get the final value of the volume, add the initial. So now we just represented, with this equation, we just represented all correspondence points given any x in the moment, right? Given any x in the moment, we get the corresponding amount of volume at that time x. And there it is. How much you have at every moment. You know how fast it's changing, and this is how much we have. It's just that we have to do that for every moment now. So we just did it for the moment at 9.68. And so we just have to do that for all the moments, say from 0 to 2 days. What do you think? You ready to start?
Everyone do 100 moments and we'll be good.
Okay, yeah, good. Richard picked up on it, right? So this is a monumental task, right? We still be working on it at the end of the semester. Okay, so this is a great starting point. It gets us the mechanics and the understanding of what generating accumulation is like. It's always about how much you had so far plus the amount added on, using constant rate of change to do that. But this is not efficient. To use this, we'd have to do it every single moment, and how big, I don't know how big these moments are, but there's thousands of them, right? So we need a new approach, right? So this is a great start. It really tests our understanding of the building blocks of accumulation from rate of change, but it's not going to be an efficient way to proceed. So I want to make sure we got it. So, and this should feel like, as we're doing this, it should feel like, oh, this is what we've been doing all along, right? We've been working on constant rate of change, and then we were working on using constant rate of change to build a linear relationship of two quantities. So now we're just doing it in a really small moment of the independent variable when the rate is changing. Are you excited as me? This is better than you think. Comments, questions? Okay. Oh, and we also have to figure out when the next assessment is, whether that's going to be Tuesday. So we'll make that next Thursday. Okay, so next assessment will be next Thursday as well, because we don't want to go too far in the material for that third assessment. So we want it to be more fresh in our mind. So we need to have that next week. Okay, so what will it look like? A more efficient approach to this. We still want to use these same principles. We need a more efficient approach that's going to get us our actual accumulation of volume function without having to do this for 10,000 moments. Okay? So this is the rate of change of oil entering the ocean at any number of time after the leak begins. This is the accumulated volume of oil leaked at any number of days after the leak begins. You know how something as fast is changing at every moment? You want to know how much of it you have at every moment. So we know the key to developing this V function from R sub V is constant rate of change. Given the rate, we know we can use, this is what we did, we use constant rate of change, and then we use V final equals V initial plus dV. So this is kind of a summary, right? And we get that change in volume by m dt. So given a constant rate, there's a little bit of accumulation, or how much we have. So that's just, that's what we've been saying all along. That's what we just finished doing, but that's just kind of a good summary. So now we want to talk about the more efficient way of doing this. So here's what we're going to do. What we're going to do is we're going to start with really big moments, unrealistically big moments. Okay? I think I'm choosing moments of 0.4. So let's look at, we're going to choose moments of 0.4. Do we have rate of change at a moment if their moments are 0.4? What do we think? Do we have what we called rate of change at a moment for these moment intervals of 0.4 days?
I'll say yes. more precisely average, we can find like an average rate of change at each moment.
Okay, but what we mean by rate of change at a moment is that the moment is small enough that we can kind of safely assume it remains constant
Oh,
without gross errors, right? Without.
yeah.
So in this case, would we have that, what we call rate of change at a moment?
I say no.
No, right? Definitely not, right? So these are huge moments, and even in this first moment, we got a huge change in the rate, and even down here, this is a big change in the rate. Okay, so what we're going to do is then we're going to look at the rate at each of these kind of the endpoints of these moments. So this is 0.4, 0.8, 1.2, 1.6, 2.0, 2.4. Okay? And so how can I represent, I want to represent this point right here exactly. How can I represent the coordinates of that point exactly? What would I write? Sarah, what would I write to represent the coordinates of that point right there exactly?
It would be 0.4 and
0.4?
then RV at 0.4.
Good. Function notation, right? Function notation gives us an exact, and then we could say that that's about, then we could do an estimate, right? 0.4 and what is RV of 0.4? What is that about? Anybody?
18.
Yeah, it's about 18, right? So this is exact notation. This is an estimate. It's about 18. Okay, and we could do that for the rest of these. Okay, we've got the exact x value, the exact y value. We could use function notation, and then we could use the y-axis to pick off approximations. Is that fair? So here's doing that. I have it at 17, but that's whatever. So 0.8, RV of 0.8 is about 8. The next one's about 1.2, or about 3. And then that's about 4. And what we're going to do then, jeez. What we're going to do is, what we need constant rate of change. We're going to have a constant rate of change in each of these moments, as crude and as awful as it is, because the moments are so big. And we're going to take the rate of change at the left side of every interval to be the constant rate for the whole interval. So here I've got what rate of change am I going to use for the first interval then? What rate of change, both exactly and approximate, I'm going to use for this first interval? Ashley, what rate of change am I going to use in the first if I'm using the rate of change at the left side of the interval?
Oh, one from 0, RV of 0.
RV of 0, which is about?
28.
About 28. So I'm going to choose that first, in that first moment, I'm going to pick off this rate that we found at the beginning of the moment and make it the constant rate for the whole moment. Good approximation or bad?
Not too good.
Not too good, right? Not too good. Okay, and I'm going to do that for all of them. So what's my rate of change in the third interval starting? So in the third interval from 0.8 to 1.2, that interval right there, the third interval or the third moment. Yasra, what's my rate of change in the third moment?
8.
About 8, right?
Yeah.
Exactly what? How would you say it exactly?
8 meters squared per day.
No, that's an approximation. So how would you say what that rate is, and as an exactly? Like how could you notate it?
Oh, like RV of 0.8.
That's right, right. So RV 0.8 represents that exact value of the rate at the beginning, and therefore for the whole thing, and then approximately 8. So this new function, we're going to create it from RV. It's called R. So just R is the approximate rate function that has constant rates in every moment. So if we had the perfect, beautiful, exact changing rate function, why did we just butcher it to death with this awful approximate rate function, this blue one that we're calling R? Why did we do that? Why do we have this nice exact thing and make it very crude and a very bad representation of what we had before? Anybody?
Is it because like we want to use that rate of change function, and it's kind of impossible to make that moment like take every single small moment.
Right.
You
right.
have to like make an approximation.
Why? So why do we have to? Yeah. So that's the question. Why do we have to?
Because there's like so many moments to take. Like you can't take every single like the way we did it the first time.
And what is it about taking a moment using the blue rate function that we can't do with the red rate function? What's the key here?
We can, with the blue function, we can find multiple rates of change at one time.
Multiple rates of change?
Or, yes, like, we can look at multiple moments at once.
Okay. So, yeah, why are we doing that? I guess I asked the right question. Why are we doing this? If we have the beautiful exact rate function, why did we make it such a poor replica of it? Why did we do that?
We were able to take like bigger chunks, I guess.
Okay. Right, why? Why do we want bigger chunks? Okay, so it's how do we find accumulation from rate? How are we going to be able to find accumulation from rate? Where does our accumulation come from? What's the mathematics of getting an accumulated amount from a rate of change? Everything we've been doing in the last couple of weeks.
You take the rate of change and you multiply it by the differential.
To get? Right? This is how we can generate variations in our quantity and then start adding these up for accumulation, right? What is this? What does this depend on? This is about what? Constant rate of change, right? Constant rate of change. The mathematics that we have to get from rate to accumulation is the mathematics of constant rate of change. In these moments, that's what this new function has for us. It has constant rate of change. So we can use our mathematics of constant rate of change to start piecing together how much we have, an accumulation of the amount that we couldn't do if the rate is continually changing. Does that make sense? So the reason for this very poor approximation, it's got constant rates. We know how to do the math of constant rate to get little changes, and then we can add up the changes.